Hi ladies, in this video we're going to go through 8H, so probably the hardest section in the textbook. And we're looking at using recurrence relations to model growth and decay. And growth and decay do occur all around us. You probably don't really notice because if you were to put money into the bank, that's growth. Okay, so your money grows. And if you were to buy a car, let's say, that's an example of decay because your car is depreciating in value. If you bought a house, usually it's growth because house prices go up. And then there's other things that go down, but putting me on the spot, I can't think of an example, but they happen all around us. And we can look at different types of growth and decay. So I'm just going to talk about the examples here. So simple interest. So simple interest just means if you were to put money in the bank and you get simple interest, you get the same amount every month or every quarter or every year. It's different to compound interest, which you kind of get interest on your interest. So it's much better to get compound interest, and that's usually what the bank uses anyway. Very rarely do you see simple interest. And another example is the new car that I said before. And that's an example of flat rate or straight line depreciation. So the word depreciation means it goes down. So flat rate depreciation means it goes down by the same amount. All right, so there's an example here. We're going to do some examples in class, or we may have already done it depending on when you're watching this video, probably after I've taught this. So, but there's some great examples here for you to look at, and very important, the main difference to what we've been doing, I might just scroll up here, you will see the first value is 0 because usually we look at, when we're modelling, VN is the value of the investment after N years. So we look at the initial value as 0, and then V1 would be 1 year after, V2 would be 2 years after, and so on. So that's the main difference that you will see in this section. And then here, V0, the price of your car when you purchased it, so 18,500. And I might just highlight this because I don't think I can underline it. The value, VN, is the value of the car after N years. So V1 is how much it is worth after 1 year, and you can see that done here. So here's your recurrence relation in action. Sorry, I was trying to think of what word I was talking about. And then you can also do it on your calculator, but on the exam, you do need to be able to show the working for a recurrence relation. You just can't write down the values. You need to actually show the steps involved, so make sure you can do that. All right, so a rule for the nth term in a sequence modeling linear growth or decay. So just going to scroll to the important part because there's an example here, but this is basically the rule that we've got here. So Vn is equal to, Vn is equal to 1,000, so your starting amount, plus n times 50. So 50 being how much interest we've got each year. Okay, $50 each year. So it's the same rule that we saw back when we did arithmetic sequences. The only difference is this time we're applying it to kind of a real life situation. And you can see there, if you wanted V20, it's 1,000 plus 20 times 5. Okay, so your starting value, and then we've got 20 years of $50 payments. So after 20 years, well, not 20 years, oh, it is 20 years. God, that's not much. You would get $2,000. Okay, so that's not much interest, but anyway, we're not here to judge. All right, so what we've got in this box, and it's very windy outside, so excuse the wind. I'll try to speak a little bit louder in case it's disrupting you. So a rule for the nth term in a sequence used to model linear growth or decay. So we let Vn, and sometimes you'll see a letter other than V, be the nth term of the sequence used to model linear growth or decay. So if we've got linear growth, the value of the nth term in this sequence generated by the recurrence relation. So this is your recurrence relation here. Whoops, let's just highlight it. So V0 is your starting value or your initial value. Vn plus 1 equals Vn plus D. So that's your recurrence relation, where D is your common difference, or how much you're going up by. And then you've got the rule associated with that, so the rule for growth. If we're looking at decay, it's pretty much the same thing. You're just subtracting D. Okay, so it's going down. So recurrence relation, rule, recurrence relation, and the rule. Okay, so there's example 22, which you can have a look at your own time. Now, geometric growth and decay. Okay, so we've already looked at arithmetic. Okay, so we remember arithmetic is the same amount each time. Okay, it goes up by the same amount or it goes down by the same amount. Geometric growth and decay goes up by the same factor or the same ratio. So remember common ratio or the same percentage. Okay, so it's going up by some factor. Let's just read this because sometimes I miss things and I don't want to. So everyday examples include a payment of compound interest or the depreciation of the value of a new car by a constant percentage of its depreciated value each year. So compound interest, you'll probably see more than simple interest at banks. So basically interest is paid upon interest or charged upon interest. So let's say something was 10%, you get 10% interest, which is pretty high, and you put in $1,000. So 10% of 1,000 is 100. So the following year, you would get 10% of 1,100, and then you'd get 10% of that new amount. So it's geometric growth. And they've given the car example this time, but it's decreased or depreciated by a percentage as opposed to a flat rate. All right, so you can see here in this example, we've got a compound interest investment of $1,000 paying an interest rate of 8%. So same rule or recurrence relation as you had for geometric sequences. So V0 though is your initial value. So you can see here, I'm just using the recurrence relation to get your values. And again, you can do that on your calculator. And then there's an example to show you decay. So remember, greater than 1 is growth and less than 1 is decay. So something's depreciating by 10%. What is that? A car. So this car is going down by 10% each year as opposed to a set amount. All right, so if we're looking at the rules, I'm sorry, I'm just going to keep scrolling so we can get through some questions. All right, so Vn is the value of the nth term of the sequence used to model geometric growth or decay. So the value of the nth term in this sequence is given by Vn equals r to the power of n times V0. So where V0 is your starting value, which we know, and for growth, r is greater than 1, and for decay, r is between 0 and 1. So that is just your common ratio, basically. All right, and there's lots of examples. All right, so let's start doing some questions. A lot to get through. Very windy evening. Don't know why that's down. Let's scroll there. Okay, so question 1. The following recurrence relation can be used to model a simple interest investment of $10,000. I'm just getting my pen ready. Sorry, I'll get distracted. Question 1. At the rate of 4.5% per year. So I'm just going to write the recurrence relation down. So V0, our starting value, Vn plus 1 is equal to Vn plus 450. So when I look at this recurrence relation, I can see it starts with $10,000 and each year I'm getting an extra $450. Okay. In the recurrence relation, Vn is the value of the investment after n years. Okay, so A, use the recurrence relation to find the value of the investment after 1, 2, and 3 years. Now, obviously, we can do this on our calculator. Well, hopefully we can do it on the calculator by now. So this is an example of an arithmetic sequence. So basically we're just adding on 450 for each term. But you, in maths, have to show how you get that. You can't always do things on your calculator. So V0 is 10,000. V1 is the previous value plus 450, which is 10,450. V2, we take the previous value, 10,450, and we add 450. Okay, so remember we're adding 450 each time. So now I'm going to get 10,900. And we've got to find the next one, I think, V3. So we take the previous value, 10,900, and I think I added too many zeros for this. Let's just get rid of one of the zeros. Plus 450. So that's 1,100. Oh, sorry. Sorry. 11,350. Gosh, I should use a calculator. Getting muddled up. Okay, so there's your recurrence relation going up by 450 each time. So question B, when will the investment reach 14,500 in value? So what you can do on your calculator, hopefully got it here. All right, so I'm just going to get a new page because, no, doing lots of trigonometry with other classes, and let's just go back. Okay, and which other one do I want? This one? Okay, so 10,000 and adding 450 each time. So 10,000 adding 450. Okay, so we've already got T0, so that's, or V0, sorry. V1, 2, 3, 4, 5, 6, 7, 8, 9. I think it was over 14,000, wasn't it? Let's just double check. Oh gosh. 14,500. Well, obviously it's going to be the next one. Let's just double check. Okay, so that's 10 years. Okay, so 10 years. Should have written it in blue, but anyway. All right, so let's have a look at question 2. So you'll see the difference between A and B. A said use the recurrence relation. That's why I had to show all that working out. B, let's just ask the question, do it on the calculator. All right, question 2. The following recurrence relation can be used to model a simple interest investment. So our starting value is 8,000. Vn plus 1 is equal to Vn plus 400. In the recurrence relation, Vn is the value of dollars of the investment after n years. So use the recurrence relation to find the value of the investment. So similar to what we did before. So V0 is 8,000. V1, the previous value plus 400, so 8,400. V2, previous value, adding on another 400, so 8,800. And V3, previous value, add on 400, so we get 9,200. All right, question B, when will the investment reach $12,000 in value? So you can keep doing this if you want to. Much easier to do on the calculator. Just before I go over, I'll make sure I know 8,000 and 400. I should probably minimize this so I don't have to keep. Okay, 8,000. Oops. Enter. And then we're adding 400 each time. Okay, so we got, I can't remember what number we had to go over. 12. Okay, so we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So it's going to take, what are we working with? Years? So 10 years. All right, question C, how much was invested at the start? Oh, well, that should have been asked beforehand, but anyway. Okay, so C, how much was invested is $8,000. And then D, what was the interest rate? So when we're doing the interest rate, okay, so we take the interest, so it's 400. Take it over the initial value, 8,000. And we can just pop that into and multiply by 100. Sorry. Converting it to a percentage, we need to multiply it by 100. Okay. You could probably do that without a calculator, but let's do it on the calculator. 40 divided by 8,000, sorry, times 1,000. No, what am I doing? 100. And sorry, 400 divided by 8,000. There we go. And then multiply that by 100. I knew I wasn't getting the right answer. That's what I wanted, 5%. You might not be able to see that too well, but there's a 5, just a 5 there. Okay, so 5% is your interest rate. So 5% of 8,000 gives us 400. So if we're having to look at it as a simple interest, it's 5%. All right, so moving on to question 3, we're looking at linear decay. All right, so a tractor costs $90,000, so V0 equals 90,000. Its value depreciates at a flat rate of 10% or $9,000 per year. So 10% of 90,000 is 9,000. So your value of D is negative 9,000. Let Vn be the value after n years. So they've already written a recurrence relation for us. So I've already got V0, so Vn plus 1 equals Vn minus 9,000. Use a recurrence relation to find the tractor after 3 years. So we've got V0, 90,000. V1, previous value, minus 9,000. Oops, equals 81,000. V2, 81,000 minus 9,000 equals 72,000. And then V3, previous value minus 9,000 equals 63,000. And you can put dollar signs in. Sorry. So the tractor after 3 years is worth $63,000. The tractor will be sold after 5 years. How much will it be worth then? Oh, we may as well just keep going. Okay, so V4, 63,000 minus 90,000 equals 54,000. And then V5, 54,000 minus, oh, I added too many zeros. Oh my God, I just noticed, sorry. For both V3, sorry, rub that out. Okay, so it's worth 45,000 after 5 years, so half its value, half its price. If the tractor continues to depreciate at the same rate for the rest of its life, how many years will it take to have zero value? So, well, we know 5 years it's lost 45,000, so it's probably going to be another 5 years to be to zero. You can do it on your calculator. You can also use the rule. So if we were using the rule, so they've given us the recurrence relation, but basically we can say Vn is equal to your starting value, so 90,000 minus n times 9,000. So if we want Vn to be 0, okay, so we're just solving then for n. So 9,000 n. You can put that straight in your calculator and solve, but I'm going to just solve it by hand. So I've got the n. And divide both sides by 9,000. So n, 9,000 here. Okay, so basically I can get rid of all those zeros. So 90 divided by n is 10. So 10 years. God, it's not good, is it? After 10 years, you've got a $90,000 tractor worth nothing. A different model of tractor costs $95,000 and depreciates at a flat rate of 12% of its original value per year. Write down its recurrence, a relation to model this. Okay, so we're starting with 95,000, so that's going to be V0. %, of its original value. So D is equal to 12% of 95,000. So if you're doing that on your calculator, to convert a percentage into a fraction or a decimal, 12 divided by 100. If you see the word of, that just means to multiply. So on our calculator, 12 over 100 times 95,000. So 11,400. So starting value V0, 95,000. You've got to always have your starting value in a recurrence relation. Vn plus 1 is equal to Vn. Because we're depreciating, it's minus 11400. All right, what's the next question? And that's it. Okay, let's move on to question 4. I don't know how many questions I've got. Can I afford to do all of them? Oh, there's a lot. Let me just have a look at question 4. I'll do question 4, and then I might do some geometric. So question 5, you can have a go at doing it yourself. Okay, so question 4. So let Vn be the value in dollars of a computer. A recurrence relation. So we've got V0 equals 2,400. Vn plus 1 equals Vn minus 300. So basically, when I look at that, the computer is worth 2,400 and it's depreciating by $300 each year. So question A. What was the value of the computer when it was new? Well, I just said it, 2,400. Pretty expensive computer, but I tell you what, back in my day, that was probably a cheap computer. Yeah, computers are pretty cheap now compared to probably when I was your age. By how much in dollars was the computer depreciated each year? So I said that before, so $300. So that's just reading the recurrence relation. What was the percentage flat rate depreciation? So we have our amount of depreciation, so 300 over our starting amount times 100. So 300 over 2,400, I'll just get the calculator up. How's this wind lately? It's just crazy. Okay, just make sure I've copied it in correctly. We want a realistic amount, so 12.5% sounds good. If I've added too many zeros or whatever, I might get 125%, which is, you'd have, yeah, it doesn't make sense. Question D, how many years will the value of the computer be $600? So you can do that on your calculator, or you can just use the rule. So that's your recurrence relation, but the rule, Vn, is just 300, negative 300 times n. Okay, so n is how many years. That's what we're going to be solving for. So we want the value to be 600. So negative 300 times n. Sorry, girls. I shouldn't be doing these videos late at night because I miss things. It's the initial value. I was just wondering why I was getting a negative value. So we've got to start off with the initial value, 2,400 minus 300n. I knew when I was doing it, I was missing something. Okay, so 2,400 minus 300n. So let's just solve for n. You can do that on your calculator if you like, but I'll just do it algebraically. So take away 2,400 from both sides. So that's negative 1,800 equals negative 300n, and divide both sides by negative 300. So n is equal to 6. Now, if you wanted to solve, or you can just keep pressing enter on your calculator. So our starting value is 2,400. We're taking away 300 each time. So that's after 1 year, 2 years, 3, 4, 5, 6. Okay, so you can do it that way as well. When I said solve, solve, and you type in your equation. 600 equals 2,400 minus 300 times n, comma n, and there it is. Okay, so you can do it that way as well. All right, when will the computer devaluate to half of its new price? So that's when it's 1,200. So I just did that before. You can work it out here, but I'm just going to go back to the calculator. So that was 654 years. It was half its price. Let's quickly write that down. So you can do it on your calculator. You can use the rule like I did before. Up to you. Okay, so I'm going to skip question 5 and do some geometric. Might just do one of each, just to allow you to have a go at doing something on your own. What are you doing? Okay. So question 6. The following recurrence relation can be used to model compound interest. So we've got our investment is $10,000, Vn plus 1. So this is just our recurrence relation. Okay, so this is a geometric sequence. So 1.045 is our common ratio, how much we're going up by. All right, so question A. All right, so we've got to use that recurrence relation for the first 3 years. So V1, I'll start off with V0, sorry, 10,000. So V1 is 1.045 times 10,000. And I'm just going to save time by just filling in some blanks here, or putting in some blanks. All right, and then we can just do that on the calculator. It's a little bit different to arithmetic, which I can easily do in my head. So we've got we're starting off with 10,000. Multiply that by our common ratio, which is 1.045. So our first one is 10,450. So I've got to bring that down to V2. So our next, oops, what did I do? Sorry, come back up here. So our next one on here. Okay, so 10,920.25, and then press enter again. So just for V3, 10,920.25, and that's 11411.66. So we're dealing with money, girls, so we just do 2 decimal places. All right, so when will the value of the investment first exceed $12,000 in value? So let's just write B here. So I'm just going to keep pressing enter on my calculator. You could set up a rule just like we did before. I find it quite fun pressing enter on my calculator all the time. Okay, so we're starting off with 10,000. We've already done 1, 2, 3. We want to know when it will be over $12,000. Okay, so we'll keep pressing enter until we get to 12,000. So there's 3, 4, 5. So 5 years. Now, if you wanted to use the rule, okay, so remember this is just a recurrence relation, but if you wanted to use the rule like I did before, okay, so here it's, I had to just refer back to it. So Vn equals Rn times V0. So we wanted Vn to be 12,000. Sorry, let's just scroll down. So 12,000, or first exceed 12,000. R is, what was it, 1.045. Power of n times your initial value, which was 10,000. Now, a little bit harder to solve for n because it's as a power, but you can just use solve on your calculator. So solve 12,000 equals 1.045 to the power of n times 10,000 comma n. All right, so it's given you 4.14. So if I said, okay, let's round that down. So this gives us an answer of n.414. If I say, oh, okay, after 4 years, no. After 4 years, you haven't quite got to 12,000. And we saw that before. We got to 11,925. So you have to round up in this case. So we have to exceed 12,000. So that's why it's 5 years. Okay, so after 4 years, just imagine if someone was paying you back money and they calculated this and said, oh, yeah, I only have to pay you 4 years. And then you just got 11,925. And you're like, well, where's my other $75? So like you have to go over. Okay, so you've got 5 years. All right, so let's move on to some harder questions because I don't want to keep doing the easier questions. Let's do question 9. So the ones I skipped, girls, go back and do them. Try to do them on your own. And just chop this top of question 9 up. Let Vn be the value in dollars of a refrigerator. That's exciting. A recurrence relation that models this. Okay, so we get the gist. Okay, V0, 1200. Vn plus 1 equals 0.56 Vn. Okay, so this is quite an interesting question because I think it's going to ask the rate of depreciation. Cool. So what was the value of the refrigerator when it was new? V0, that's when it was new, 1,200. B, how many years will the value of the refrigerator first be less than 200? So you can do the rule, if you like. So Vn equals 0.56 to the power of n times 1,200. We want it to be less than 200, so we'll just write 200 and solve for n. You can keep pressing enter on your calculator as well. So let's do it both ways. So I'm going to do solve first. 200 equals 0.56 to the power of n times 1,200, comma n. So n equals 3.09. It's not quite below 200, so we have to round to 4 years. Now, if I was to do it on my calculator, I just did it on the calculator, but 1,200, let's scroll back up, is our starting value. So that's V0 multiplied by 0.56, so that's V1. So after 1 year, it's now worth $672. 2 years, $376. 3 years, $210. So we haven't quite reached that $200 mark. Then 4 years finally drops below. Okay, so you can do it that way, or you can use solve like I did before. Okay, so C, when will the refrigerate devaluate to less than half its new price? I don't know whether the new price, it means the previous question, or 1,200, because that's what it did before. It's a bit weird. I should check the answers, but I'm just going to devaluate to its new price. Okay, well, I think its new price is 1,200. So we can, again, set up an equation. So half of 1,200 is 600. 0.56 to the power of n times 1,200. So n is equal to, now I'm going to show you a sneaky way of, you can just scroll up. Obviously it's a bit easier to do on a computer, but you can use your cursors on your calculator and just change that to a 6. Okay, so n equals 1.195, and we want it to be under. Okay, so at 1.195, it's not quite under, so we're going to have to say 2 years. Sorry, a bit of a blank there. And you can see if I scroll up, that's our starting value, 1,200, 1 year, 2 years. Okay, so after 1 year, it's not quite half, so 2 years, definitely below half. All right, what was the percentage rate of depreciation? So R, or your common ratio, I don't like they've used capital R, but anyway, is 1 minus your interest rate over 100. So our value of R for this is 0.56. 1 minus R over 100. So that's what you do for percentage rates. And you can just solve for R on your calculator. So this is just going back to geometric sequences when we had percentage increase and decrease. Just a shame that they always use the same. Oops, I didn't say solve. They always use the same letters, which is sometimes annoying. Comma R. Okay, so 44%. When you think about it, 0.56 is less than 1. So 1 being 100%, okay, a whole. So if you're greater than 1, obviously it's growth, okay, you're greater than 100%. 0.56, you could say, well, that's just the difference, 1 minus 0.56, so 44%. I'm just thinking if there's another easy way to do that. Okay. Oh, let's just do question 10 because it's the last question. And I'm sure it's nearly 9:30, girls. My son's downstairs probably loving being on the PlayStation so late. The following recurrence relation can be used to model a compound interest investment of $30,000 paying interest compounding at the rate of 3.5% per year. Cool. Use a rule to find a value of the investment after 15 years. So we've got V0 equals 30,000. So this is just your recurrence relation. Now, your rule, let's do it in a different color, is Vn, your value, 1.035, your common ratio to the power of n, times your initial value. So we did this when we did geometric sequences. It is also in your notes at the start, okay? So we want to know the value after 15 years. So V15 equals 1.035 to the power of 15 times 30,000. So 1.035 to the power of 15 times 30,000. Okay, so we're working in dollars here, so we only need to do decimal places. Make sure you can round. If you have trouble with rounding, always do more numbers than you need to. So let's say I had trouble with rounding. I'd do 4 decimal places, and then I would do my rounding. Okay, so 46. Okay, so we're dealing with money. We only go to 2 decimal places. B. The following recurrence relation can be used to model the reducing balance depreciation of a motorbike purchased for $4,000, depreciating at a rate of 17.5% per year. Use a rule. Okay. So I'll get my pink pen. So we've got V0 equals 4,000. Vn plus 1 equals 0.825 Vn. So your rule, Vn, the value of the, boat? Motorbike? Okay. The value of a motorbike after n years after it was bought for $4,000. That's a cheap motorbike. Your common ratio or your rate of decay to the power of n times your initial value, 4,000. So n is 4, so we're going to do V4, the value when in the fourth, after 4 years. 0.825 to the power of 4 times 4,000. Let's plug that into the calculator. 0.825 to the power of 4 times 4,000. So that's 185,300. Easy one to round. All right, so girls, a few questions I didn't do, so make sure you go back and do them if you haven't already done so. But quite tricky, these questions, but please make sure you understand them and ask for help if you need it. Okay, bye.